Hi guys, thanks for joining me again. This is the Renegade Mathematician, and we're continuing yet again our discussion of determinants. And what we're going to be talking about today are minors and cofactors. And the use of this, the utility of minors and cofactors, is that it gives you a more practical way to calculate determinants. So, without further ado, cofactors and minors. Alright, quick note. In this discussion, we will be departing from the definitions that Ch1.5 uses, and thus the proofs presented herein will also be different from those presented in Ch1.5's text. This will be discussed further at certain points in the video, or another video, whatever. Okay, so a definition with a note, and let's start off the definition. Okay, given a determinant D, we define the minor of the entry a sub ij of D to be m sub ij is equal to something that looks vaguely like a determinant, right? Where alpha ranges over all permutations on the set 1 through n such that alpha of j is equal to I. And what I want you to notice about this definition is, if you go searching for a sub alpha j, you're not going to find it. You'll notice that it's missing. And alpha of j does not appear in the inversions either. It's not there. Okay? So note, this definition resembles the definition of the determinant, and although it is not the determinant D, it is another determinant. Notice that neither j nor alpha of j occur in this formula. You should look for it, see that it's not there. In fact, what we have done is we've removed it. Okay? Since j does not occur, then no entry from the jth column will appear in the formula. That's important, right? Because a sub alpha of j doesn't appear in there. There's no entry from the jth column. Since alpha of j is excluded and alpha j is equal to I, then no entry from the ith row will occur in the formula either. Okay, so what we've done is we've excluded entries from the jth column and the ith row. The effect is that we have eliminated the ith row and the jth column from the determinant D. And notice how we've done that on the determinant below. Okay? The determinant of the matrix consisting of the remaining entries is the minor, m sub ij. So, actually, it's probably best in practice to think of the minor in that way. You cross off the ith row and the jth column, and then what's left, that's your minor. However, for the purpose of doing proofs, we'll have to use the terse definition that's less practical to use to make calculations, but is more useful in constructing proofs. And that's just the way it goes. So anyway, moving on. Okay, here's an example. So given the determinant 1, 2, 3, 4, 5, 6, 7, 8, 9, the minor m sub 1, 1 is the determinant 5, 6, 8, 9, and the minor m sub 3, 2 is the determinant 1, 3, 4, 6. Here's how we get them. Take, for example, m sub 1, 1. We get that by crossing off the first row and the first column, right? And the result is the rest of the determinant that wasn't crossed off. That's the new determinant, the minor m11. Okay, moving on to the other one, the determinant 1, 3, 4, 6. How do we get that? Well, I is 3 and j is 2. So we cross off the third row, second column. And what's left is what comprises the minor. That is 1, 3, 4, and 6. Okay? Now we have another definition here, and this one's pretty easy. So given a determinant D, we define the cofactor of the entry a sub ij of d to be capital A, and this is important, we use capitals for these, sub ij, which is equal to -1 to the power of I plus j times the minor, m sub ij. So the only difference between the cofactor and the minor is that we've also got some power of -1, so it's going to affect the sign. Okay? That's the only difference. So note, in the text, Shilov defines the cofactor another way. So I'm differing from Shilov again here, and then proves that capital A sub ij is equal to that power of -1 times the minor. In our discussion, we define a sub ij to be equal to that power of -1 times the minor, and we'll eventually prove Shilov's definition. So either approach is valid, but I prefer my approach, So the idea is that Shilov starts at point B and then gets to point A, and what I would rather do is start at A and then go to B. Anyway, and that's the video. Hope you guys enjoyed it. If you tune in next time, we'll go ahead and prove another important theorem called the cofactor expansion theorem, and that is a very useful tool in calculating determinants because it can deconstruct large determinants into smaller determinants. So we'll see you next time.